Well, first, happy birthday to Nicola, that in Minnesota Jim Face would call you El Gran Nicola or something similar. Something. And, as Irene pointed that we were the people that knew Nicola first in this audience, but we realized that I'm really the second. Irene was there before I arrived. I was at Quran at the time. So happy 50 plus. Okay, I was assured like 10 times that this had to be a lecture for a large mathematical audience. And I don't see any face that's not an expert in PDE. So anyway, you're going to swallow the first 10 minutes or something like that of general knowledge. The talk is really split in two parts. The first half, I would like, I like to say some general things about, what is important for every boundary problem, a little bit the history of how it evolved. And in the second part, I like to describe a chunk of work that I have been doing with some of us too through the years, and how the ideas evolve, because there is a continuity in this sequence of papers. Okay, so let me explain you what is the Laplacian to start with. So if you want to try to describe what is diffusion, the first thing you look at is the Laplacian, right? And the best way is to describe it by a random walk probabilistically. I think that's the one that I like best to explain why Laplacian is diffusion, right? And so in one dimension, the Laplacian is just the second derivative, and you can think on the Laplacian as being the following. You have a bunch of particles that jump right and left randomly, okay, and so you want to do a balance equation, okay, so you have your pile at the point x0 plus h, x0 minus h, and randomly at some rate the particles are set right and left, and you want to check what is the balance, what is happening at x0, right? And so there is a gain. An important aspect of diffusion is the concept of a gain and loss. And there is a gain that comes from the particle jumping from the right and from the left. And since half of them go to the right and half go to the left, you at x0 only gets half of u of x plus, of a multiple of u of x plus h, and half of a multiple of u of x minus h. But the particles jumping from u0 go right and left, okay? So basically, this is, if you look what happens in time is that the change, the way that u at x0 evolves in time is according to the gain minus the loss, okay? And this is a second order incremental quotient, so if you want to do an infinitesimal version of that, this has to be uxx, okay? In higher dimensions, the first time I saw the Laplacian maybe 46, 43 years ago, 42 years ago, no more, 45, 47 years ago. And when I was told that this was the Laplacian, I had no idea. I mean, I knew that was the real part of an analytic function satisfy that, and so it was something important, but I didn't understand it. And really, if you want to understand the Laplacian, you have to reason like in one dimension. In other words, you have to look, and think that the Laplacian is really the average, right? Now you have your particles concentrated at the origin, and you have a bunch of particles around, and all the ones outside are jumping here, and the ones here are jumping out. And so you can argue that in some sense, you can argue line by line if you want, or something like that, and see that the Laplacian is really the average of u outside minus u at the origin, or if you want to think on second derivative, the average of the radial pure second derivative, okay? And so if you look at this way, then you immediately understand why, for instance, the Laplacian is invariant under rigid motions and why it's special. Okay, so so basically that also tells you that what is a process of diffusion is a process where the variable under consideration, right, is comparing itself with the surrounding density, right, and tries to revert to that surrounding density. In other words, tries to, you know, if in other words, u looks at the Laplacian of u, which is the difference between the surrounding average and itself, and if that is positive, it grows. If that is negative, it decreases. Okay, and so in some sense, any process of that way can be integral diffusions, can be you know, any type of anomalous diffusion. In some sense, is an elliptic process or a diffusion process. It has that. In some sense, you feel that has that property that, you know, you compare yourself to whatever surrounds us, and you sort of want to comply to everybody else. You don't want to be different. So, you know, if you look at the viscous flow, the Laplacian in the Navier-Stokes equation is the same phenomena, right? In other words, you have a particle, and if a particle tries to speed up, right, the surrounding particles sort of try to break it. And when you express that, you express it by the term Laplacian of u in a viscous flow. Okay, and in elasticity, whatever, there is always implicit this idea of reverting to the average. Okay, so so what I want to discuss now is how this idea appears in not just in a standard, you know, density or a standard fluid, but how it appears when you are working, when the diffusion happens on lower dimension, on surfaces in Rn. Okay, and there are basically the two main cases that I want to discuss and that intertwingle a lot is minimal surfaces and free boundaries. Okay, so so as I say here, this happens not just in densities, temperatures, financial mass, but also appears in a much more subtle way in the configuration of geometric objects like minimal surfaces or stationary or dynamic interfaces. Okay. So let me tell you a little bit the story of the familiars of minimal surfaces. Okay, so so let me start with minimal surfaces, right? So if you look at the minimal surface, the Euler-Lagrange equation for a minimal surface is zero mean curvature. Okay, and zero mean curvature is like a geometric Laplacian. In other words, zero mean curvature consists on the following. The picture is not too clear, but you know, you have a surface, right? And for the surface to be minimal, right, you take the tangent plane to the surface, and so you can express the surface in coordinate in the tangent plane. And so if you look at the quadratic polynomial has two eigenvalues, right, in the plane, and the two eigenvalues are the curvatures, the principal curvatures of a surface. Okay, and so the zero mean curvature means that the sum is the Laplacian in tangential coordinates. In other words, zero mean curvature means that at every point you take a tangent plane, you write the Laplacian in the tangent plane, and it has to be zero. So in some sense, it's a geometric minimum. The zero mean curvature is a geometric Laplacian. Okay, and so you expect, in some sense. So one of the things I want to discuss is why being like geometrically harmonic, right, implies regularity for this surface. And movement by mean curvature is like a geometric heat equation then. In other words, at every point you have this curve, let's say, that is shrinking at a point because at every point, right, the surface moves with velocity proportional to the mean curvature. Okay, so it is basically like the heat equation for surfaces. Okay, if you want to look at a similar example for a free boundary, I think the easiest thing to look at, or the most familiar thing to look at, is the Stefan problem, right? You have a solid-liquid interface, right? Basically, the simplest model is that you look at, they have a region where there is positive temperature, a region where is negative temperature, right? And so the interface, the configuration evolves in the following way. In the liquid part, there is heat diffusion. In the frozen part, in the solid part, there is heat diffusion, right? And then the free boundary moves proportionally to the injected heat. In other words, to melt the solid part, you need to have, to provide the latent heat, and the latent heat is proportional to the jump on the normal derivatives. Okay. So why should such a surface? What is the hidden diffusion in this process? So one can make a sort of a very naive argument and say the following. I say, well, what happens is the following, right? You have the diffusion of the temperature in the negative and the positive part, and then if you look at the interface, if you study the property of harmonic functions or the heat equation in domains, you know that if you have the heat equation in a domain like this, and it has like a bulge here, then you put temperature here, then the temperature coming from this way is going to decay much faster, right? Like if you have an angle, then harmonic function has a higher decay, while here the domain is surrounded by higher temperatures, and therefore the normal derivative of the temperature going in this direction is going to be bigger than the one below. And so this is again the sort of the diffusion process we were saying before, but sort of more in a global way. In other words, you have this surface, and this surface, then if the surface sort of lag behind and forms like a finger, then it's going to be accelerated by the increase of heat in this side and the decrease of heat of cold in the opposite side. Okay, so basically this is the mechanics why one should expect that a surface in the Stefan problem, following the model of the Stefan problem, the solution should have a smooth interface flowing around. So you can think this iteratively, right? You can say, okay, let me not move the interface for a while, right? You can say, okay, here I have, at this time, I have this temperature, right? And then I'm going to keep frozen the free boundary, and the temperature is going to increase, right? So here the temperature is the same as before, but the slope is bigger. And then if I let free the free boundary, since the slope is bigger, the free boundary is going to move. So one can think on this phenomena sort of in an iterative fashion. Okay. So this is of course a very simple model, right? I mean, there are much more complex models for the Stefan problem, but I want to, so if you are presented with this problem the first time of your life, and you look at it and say, okay, this is a nice idea that you are looking at what happens around you and try to, but how do you express this globally, right? How do you extract from a very simple mathematical model that says the temperature flows and the free boundary move proportional to the normal derivative, how do you, find a mathematical way to showing that indeed that surface regularizes, okay? In other words, how do you do that? And so, in some sense, this goes, as we know, as the label of Harnack inequalities, oscillation lemmas, and so on. And I think, in good part, the main ideas on how to materialize this diffusion regime were developed by de Giorgi when he developed the theory of regularity for minimal surfaces. Okay, so let me tell you, although you may know how did the theory evolve. Okay, so In fact, I think a posteriori one could, always make a ellipticity theory without talking about equations. In other words, without talking about the fact that you have this family of surfaces that for some reason, right, if you perturb them in one region, right, then what Harnack inequality says in some sense is you have this family of surfaces, let's say minimal surfaces or some kind of equation that have the property that you perturb them in one point and the effect is felt instantaneously all around with comparable intensity and in the same direction. And I think that is in some sense the secret of ellipticity. Okay, this is the secret of ellipticity for free boundaries. The secret of ellipticity for minimal surfaces is what makes a process elliptic. Okay, and there are three methods to look at elliptic equations. Right, one is if you have linear or close to linear equations, then you have superposition methods, and that means Fourier transform, means potential, etc. If you don't have that, then there are the equations from continuum mechanics where you work with by energy considerations, right? In other words, by truncating, multiplying, etc. And maybe the hardest of all is by comparison techniques, because energy equations in the calculus of variations are infinitesimal, but they are global in some sense. If you think all the methods you use consist of multiplying, integrating by part, and so on, so they are hidden some global element. Okay, if you look at equations like fully nonlinear or bounded measurable coefficient non-divergence, then that is to relate the infinitesimal to the global, let's say, is much more difficult. And in fact, the only way that after many years people were able to relate them, that is the Krylov and Safanov technique, was through an equation which is non-divergence and divergence, which is the Monge-Ampere equation, right? In other words, the Monge-Ampere equation is an extremal equation for non-divergence problems, but at the same time, right, it is a divergence equation, and that is expressed on the fact that it is the Hessian of the determinant of the gradient map, and therefore you can sort of has this integral flavor that says that the image of the gradient map is determined by the right hand side of the determinant. Okay, what happens in the theory of minimal surfaces? Well, there is of course a very old theory of minimal surfaces. It was basically what is classically called the plateau problem. In other words, people look at minimal surfaces or as graph or as images of a disk. There is an enormous amount of literature where you take, it's like a soap film, right? People will take, let's say, a circle and look at a map into R3 of a circle and look at those maps such that the image minimize areas. And so this was a very delicate and beautiful theory, but it was in some sense very confined, and people start to realize that there were many problems where what one wanted is sets whose boundary has minimal area. Okay, see, the simplest example you can give is if you want to, just take a domain, and suppose you want to wrap it, right? You want to wrap it with, some tin foil or whatever that has minimal area, okay? In some sense, the idea of develop this theory came with, I would say, in the 50s, with the general idea of looking at problems in partial differential equations where you look for weak solutions, okay? Like the Lax-Milgram theorem is a typical example of a problem where you want to solve some nonlinear or linear whatever PDE, and you resort to a functional analytic structure where you find something that you are willing to call a weak solution, right? And if you construct a weak solution, then you have reduced the problem to solve that the weak solution is a really nice solution, okay? And so I think what's remarkable, Cacciopoli and De Giorgi, basically, De Giorgi with his natural, fearless approach to mathematics said, okay, for me, what I'm going to look for minimal surface, I'm going to look at sets of finite perimeter, and that basically one of the ways you can define it is, you suppose a set has finite perimeter if it is the limit, the characteristic function of if the characteristic function of this, you look at polyhedra, and you look at the characteristic function of polyhedra for those polyhedra whose boundary has uniformly bounded area. And then you look at L1 limits of that. So you are taking the characteristic function, you look at L1 limit of that, and you say the set has finite perimeter if it is the L1 limit of polyhedra with bounded perimeter, with bounded area. And so you get an object, right, which, whatever it is, is a set. You can say that it's a set whose gradient has bounded variation, for instance, or similar approaches, right? So, for instance, suppose you want to wrap a set with a set of minimal area, then you take, there are here, if the set is bounded, there are polyhedra that have finite area, so you want to look at the infimum of the areas among all the polyhedra that surround that set, right? Want to take a sequence of polyhedra that have areas decreasing to the minimum, right? That family of sets you can show that is compact in L1, and therefore there is a limit whose area, right, in some generalized sense is smaller or equal than all the others. So there is your set of finite perimeter. So to construct a wrapping is, more or less, they have to develop a little bit of theory, but you just build it, okay? And that's it. This is the remarkable theorem, right? This object that you constructed, that it was the limit of polyhedra in L1, right, is an analytic surface, right? For any dimension, when you reach dimension A, then there can be singularities, and the singularities have Hausdorff dimension n minus 8, okay? So I think this is one of the most remarkable, right, developments of the theory of partial differential equations. So what are the main ingredients in the regularity of the theory of minimal surfaces? Okay, there are basically two ingredients. There are different ways, but I think there are basically two ingredients. It's a monotonicity formula and classification of blow-ups, and linearization and improvement of flatness, which is something that we will see again and again as the discussion goes along. So the idea behind the blow-up approach is the following. So it says, if you have an area minimizer surface, right, and you make a dilation of the surface, that's again area minimizer, right? Has this area with respect to all its comparison. And if you expect that your minimal surface at the origin has a tangent plane, and you start to dilate it this way, then at the end of the day, globally you will have a plane, right? So you argue the following way. You can say, okay, if I know that all global area minimizers are planes, right, that means that when I started with an area minimizer around a point, it had to have a tangent plane. Okay? So how are you going to show that your limits of blow-ups are going to be planes, right? And so the help comes from a classical beautiful monotonicity area that says, that if you look at the area of the minimal surface in the ball of radius r and normalize it by r to the n minus 1, this quantity is monotone in R. I think it's something important that of all the monotonicity formulas that we have been looking, so the important thing of a monotonicity formula is some sort of measure of entropy when you go away from a point. In other words, you have a point, right, and you look at your solution in a very tiny neighborhood, and let's say it's a plane or it's a polynomial In the case of Almgren, monotonicity formula is a polynomial of degree k, or whatever, okay? And then as you go away, right, the surface starts to disorganize itself, right? But okay, one could say a convex surface disorganizes itself, and nevertheless the area will decrease, right? But the fact that the surface under consideration satisfies a particular equation, right, makes this organization in such a way that this ratio grows. And in that sense is that I'm saying that one should think about monotonicity formula in some sense as entropy formulas, as entropy, increasing entropy, radially increasing entropy quantity, okay? So for a minimal surface, then this quantity is increasing with the radius, which means that it has a limit when r goes to 0 and a limit with r goes to infinity, okay? And so if you perform a sequence of dilations of a minimal surface, at the end this quantity will be constant, will be the limit at the origin, okay? And so there is a theorem that says that the monotonicity ratio becomes constant for blow up, and also then that global solutions with constant monotonicity formulas are really cones. And in dimension less than 8, minimal cones must be planes, okay? So that means, so now we are sort of in a position to try to apply our idea of saying I take a point, I make a dilation, I look at, so this cone is what the picture was at the origin to begin with. So in some sense at the minimal surface you have or a cone or a plane, okay, as some sort of asymptotic limit. Now we know that cones are out of the question if we are reasonable and don't worry too much about singular points, right? But then there is, okay, asymptotically is a plane, but what does that mean? Okay, and so so then comes the second question: is if minimal surface around the point is asymptotically a plane, right? Is it a smooth surface nearby? Okay, and this is, for instance, one of the ways this is carried out is through non-homogeneous blow-up. In other words, when a minimal surface is very flat, is very close to being harmonic, because you are starting, heuristically, you are starting to compute the Laplacian in a system of coordinates which is more and more horizontal. So the minimal surface, that is the mean curvature equation, differs from the Laplacian in less and less, okay? And so there is this beautiful idea of non-homogeneous blow-up, or approximation by harmonic functions, that says, okay, let's take a very flat minimal surface, right, and I'm blowing it vertically to height 1, okay, and let's try to prove that, okay, this blow up, suppose that this is flatter and flatter, and we blow it up higher and higher, right? Let's try to prove that in the limit, then we get a graph of a harmonic function, okay? So you can prove that, right? You prove that if you do a sequence of a vertical family of blow-ups of a Skinner and Skinner minimal surface in the limit, this thing that seems to be topologically complex ends up being the graph of a harmonic function. But if you have a harmonic function in the interval 0, 1, which is bounded, near the origin has all the derivatives you want, okay? And therefore, this function here is, you can make this function here much flatter than this ratio, okay? Right? Because here the function starts cubically, whatever, no, polynomial, linear plus quadratic, right? So you can flatten, so you can see that the blow up of your minimal surfaces really is contained in a flatter coin, okay? And so you renormalize and start again, and renormalize and start again, and that way you can show that if your minimal surface is flat enough, then you can put it in a sequence of flatter and dyadically flatter domains, which means that your minimal surface really there is a C1 alpha surface. That is, at every point separates from a tangent plane with an r to the 1 plus alpha speed. Okay? So this is the other ingredient that comes from the theory of minimal surface, this idea of improvement of flatness. Wow. Okay, I'm going faster about this because if not I won't be able to talk much about it. So in free boundary problems you can do basically, many of the techniques you use are very similar to this, okay? So some of the examples I'm giving now we just hear from the other people, right? So in these examples, right, there is basically a similar technique, right? For instance, if you take what I say balloon in a box is the obstacle problem, right? You have a balloon is constant mean curvature, right? If you put it in a box, right, then it will stick to the side here and here, here and here, right? Okay, and so this is a free boundary problem. Here you have constant mean curvature, you have a part which is flat, here you have C11 separation, right? And so what you do in a problem like this, or like the obstacle problem, that where you have C11 separation, right? Then you basically use the same techniques. You take a point. So here, what is the natural family of dilations? Here, the natural family of dilation is quadratic in U, because U starts here, or you expect U to start here quadratically, right? The mean curvature of the Laplacian is positive, and here becomes 0, so it's quadratic homogeneity, right? And so you do quadratic. So what are the main ingredients for a free boundary problem of making this blow-up approach? Okay, so the first two ingredients you need are optimal regularity and non-degeneracy, right? Optimal regularity, that tells you that if you try to blow up with the correct homogeneity, right, you will be able to do that you can rescale and you will get something which is non-trivial, which is bounded. And non-degeneracy tells you that at the end your knowledge of the free boundary has not been erased, because if your solution is much flatter than quadratic at a point and you make a quadratic blow up, in the limit you get identically 0, there is all of your information about the free boundary has been lost. Okay, and so basically, so non-degeneracy will allow you to recuperate the information of the free boundary when you started with, okay? And so you have to look at the geometry or classifications of blow-ups, go back, look what is the asymptotic picture. If that is a half a space, means your free boundary is regular, and then you have to use different techniques depending on your problem, right? Sometimes it's improvement of flatness, sometimes it's boundary Harnack properties and so on, and you end up with a picture which in general will be a smooth manifold plus singular points. Okay, and one ingredient which is important, often important, or is the saving grace of the problem, is that there is in this problem some monotonicity formula. And so the main formulas that are often used are the Almgren monotonicity frequency formula for harmonic functions, so a bunch of different monotonicity formulas associated to the ideas of waves, and the formula that was mentioned before that I wrote with Alt and Friedman. So I want to say something before I start my part, the written part of the lecture. I want to say something, which is that in all of, or in many of these free boundary problems, although the curvatures and minimal surface are never mentioned, they play an important role. In other words, there is often some sort of connection with curvature. For instance, in the obstacle problem, when you blow up, solutions become convex. So the level surface of the coincidence set, all the level surfaces are convex surfaces. In the optimal shape problem that was discussed before, the free boundary has positive mean curvature. You make a little computation, and at least for global solutions, the free boundary has positive mean curvatures, because the gradient is subharmonic, is 1 on the free boundary, and is smaller or equal than now everywhere. And that implies that the surface is boundary. And the other example I want to give, which I was going to discuss more in detail, is sort of variations on the Landau-Ginzburg problem. So can we raise this now? Okay. Okay, so more or less I have until what, 10, I think it's it?
5.
What do you mean 5? I went up, bring my 5, 10.
No, I can't see.
I see.
You negotiate on that.
Henrik is a tough negotiator. Okay, so at this point I just I wanted to tell you about some work that, as I said, I think is illustrative of how things work, because I did through the years as things were appearing and how they are related to each other. Okay, so so when I was at the Institute for Advanced Study, I had Langlands next door, and so I have no choice but to learn about the Ising model. So the Ising model is a magnetization model, right? You have sort of an array like this, and you have particles which are magnetized at plus or minus, and so on, right? And you want to describe this some way, okay? And so the simplest model is that you have the plus and the minus separated, and there is a neighbor-to-neighbor interaction. And that means that you are a plus, but there are more surrounding particles which are negative than positive, you turn into a negative one, okay? So in some sense, the interface between this model, right, is determined just by sort of just by the structure just at the interface, okay? And so there is a continuous model for that, which is called the Ginzburg-Landau equation, right? And the idea of the Ginzburg-Landau equation is the following. So you have two faces, right? And so you have a function u, which is 1 or minus 1, indicating in which phase you are, okay? So you have here a phase 1 and a phase minus 1, and so you have a function u, okay? Which in principle will be a Heaviside function, but since you want to give some room at the interface, or what's going at the interface, instead of being a jump function, right, it's a function u, right, which is 1 and minus 1 in one phase and minus 1 in the other, and something intermediate. In other words, saying, okay, let's assume that there is a little interface in between, right? And so my function u is going to be 1 and minus 1 is going to go through 1 and minus 1 in between, okay? And then you say, okay, what I want my function u to minimize, right? So it's what is called a double well potential, W of u, right, where your W is going to be 0 when u is 1 and 0 when u is minus 1, right? But in between you're going to pay, right, because you don't want to have interface, okay? So in between you're going to pay, so your W is going to be something like this, right? And then you want to put a 1 over epsilon to make this more and more expensive, and at the end you will end up with 1 and minus 1. But if you just put that, then you end up with any characteristic function of a set has energy 0. So you have to put a way to pay for the interface, okay? And so the way to pay for the interface is by adding epsilon the integral of gradient u squared, okay? And why does this pay for the interface? This pays for the interface. In fact, let me put here, call this function w squared, right? And if I call the function w squared, you are paying for the interface, because if uses controls the integral of 2 gradient u right, times W of u, okay? And gradient u times W of u, right, is the gradient of a potential of u, right? You can think of W being f prime, where f prime is a potential. W was going from, W was this, so the integral is something that goes like this, right? Okay, and so you can think of this as being the integral, the integral of gradient of f of u. And so this is controlling the price of jumping from 1 to -1. In other words, f of u is identically 1 when you have gone to the right, identically -1 when you are on the left, and so you are paying for the transition. And in fact, if you minimize this, then these two quantities become comparable, and indeed, you get some sort of phase transition argument. And so when you let epsilon goes to 0, at the end, then the interface is forced to be not just anything. Suppose I put data 1 here and data -1 here, then the interface ends up being a minimal surface. Okay, so you have a minimal surface, and if you add here, you can make a parabolic equation of this. You can make ut equal Laplacian of u, etc. And then what you have is a surface that moves by mean curvature. So if you do a parabolic equation out of that, you get a movement by mean curvature. So minimal surface, and movement by mean curvature. Okay. Now, if you look at if you look at the literature on minimal surface, on phase transition and so on, then they all start with a much more generous model. If you look at the work of Five or Leibovitz and so on, you have your interface, you have two medium, there is action in both media, and things happen, right? And so if you review this scaling, and do it slightly different, then you end up with an equation where you have the minimal surface in between, but on both sides you are left with non-trivial potentials. You end up with gradient u squared if you have diffusion on one side, and gradient u squared if you have diffusion in the other. And that's why one thing that we look, it's a paper I wrote with Carlos Koenig, Athanasopoulos, Koenig, and Salsa, right, was the issue of what can you say of the interface if you have equations on both sides. So you look at the problem of the following problem, says, okay, what I want now is, let me put a simple configuration, let me put here u equal 1, here u equal -1, and so intermediate I have an interface, right, so that gradient of u squared, that u is harmonic here, u is 0 here, but I also want to minimize the perimeter of this set. In other words, I want to look at minimizers of the functional gradient u squared plus the perimeter of the set, let's say, where u is bigger than 0. Okay? So we look at this problem. What is it? Okay, I should keep one of these. So we look at this problem, and the first thing we realized after a while was that gradient u squared was secondary here. In other words, if you try to scale this functional, then if you say, okay, I'll try to rescale this functional preserving this energy, then you have to rescale u as Helder 1/2. You have to do u of lambda x over lambda to the 1/2. Okay? So, but if you have this configuration, you expect U to be linear most of the time. You have a harmonic function that becomes 0 in a nice surface, then U should be linear. Okay? So the conclusion of that was that we should try to just go and try to show that U is linear, because if U is linear, then we are in business. And let me explain you why are we in business, right? So the first thing is that, okay, the natural scaling is U C1/2. So the first thing we prove is that indeed the minimizer on this problem U was C1/2. Okay, and this just comes from the natural scaling. Okay, so you prove that U is C1/2, but then you do more carefully your perturbation. U is C1/2, and also the free boundary condition you check that it is that gradient U plus a square minus gradient U minus a square, right? This is a standard free boundary condition when you have a jump between two faces, right? Have to be proportional, have to be equal to the curvature of the free boundary. So here curvature applies. Curvature of the free boundary.
You mean the mean curvature?
The mean curvature, yeah. Mean curvature. Okay, and also if we work a little bit harder and we prove that in fact along the free boundary gradient of U plus and U minus have to be bounded. And then once you prove that, the problem is finished, because a beautiful theorem of Almgren that says that if you have a minimal surface such that the mean curvature is bounded in the sense of perturbations, right? Then the solution is C1-alpha. Okay, so basically what you get is at the end for this problem, what you get is that the solution is C1-alpha in each side, because when the surface is C1-alpha, the normal derivative of a harmonic function is C-alpha, so the solution is C1-alpha in each side, and the separating surface is smooth, C1-alpha, you can improve that, except possibly at singular points, which are n-7. Okay?
So you mean when the gradient is bounded, the perimeter is the dominating.
The gradient is bounded, then you get that the mean curvature is bounded. So you have a surface with mean curvature, almost C1-1, right?
Yeah, but before going there, I mean, you have to have something else, because
The gradient bounded you get just by making perturbations. You make careful perturbations, and you see then that the gradient has to be bounded on both sides.
because almost minimizer.
Pardon?
It's almost minimizer of minimal surfaces.
No, it's the other way around. It's the other way around. You have this solution, right? And you do, it's okay, it's minimizer of minimal surface. So what you have to do is you have to do perturbations where you don't change too much the surface. Okay, you can do perturbations where you don't change too much the surface, so the change on the surface is negligible, and that allows you to control the gradient U at the boundary, okay? So you do perturbations like in the standard. If you don't have this, you have the jump in gradient U squared, you do you have the monotonicity formula, you do perturbations, and you show that the gradient is bounded. And once you show that the gradient is bounded, then automatically you have bounded curvature. Okay, and bounded curvature is a very nice, almost like a minimal surface. Okay. So sort of at the same time, I started to look at the associated movement by mean curvature. So we look at movement by mean curvature. Let's see, let me see. Yes. So I start to look at movement by mean curvature. By mean curvature. Right? And as I said, if you look at the works of Five and Lewis and so on, then when they talk about phase transitions, what they have really is a much more complex model where there are non-local interactions. Usually what they say is that you have this, you have the phase 1 and the phase 2, and then you have an energy term, which is like a kernel J of x minus y, u of x minus u of y squared, etc. Okay? And so I said, okay, so let's look a little bit more careful at, so this indicates that there is some sort of a non-local ingredient there. Let me tell you that they all of a sudden ask this kernel to have finite first moment. And then they end up with an infinitesimal quantity for the interface. An interface basically with mean curvature for the interface. Okay? So there are different ways in which people look at movement by mean curvature, and there is one which in some sense is due to Merriman and Osher, but is motivated by the theory of, at least for me, motivated by when the George does the theory of sets of finite perimeters, what he does is he convolves with the Gaussian. Okay? And so one can construct movement by mean curvature as a segregation model. Okay? So a segregation model will be the following. You have, population here, which I'm level with a 1, a population here, which I level with a minus 1. And you want to see, a model for how this evolves, okay? And so a model for what this evolves is, so let me call, at time t, let me call h of t the function which is 1 and minus 1, okay? So it's like the sine function, okay? So you start with h of 0, right? And then you convolve with a very narrow Gaussian, g epsilon, okay? So you convolve with a narrow Gaussian, you have 1 and minus 1, and then you convolve with the Gaussian and you get something which is smooth, right? So it is like you are allowed the populations to mix. So you are allowed the population to mix for a little time, right? So you have here, let me put it like this, you have here 1 and minus 1. If you convolve with the Gaussian, right, the level surface 0 of the Gaussian will go a little bit inside, because since this is curved, when I compute the integral of the Gaussian, center here will be a little bit more of 1 than of minus 1, right? If this is curved this way, right, over here, when I convolve, when I have more minus 1 than 1. So in this region, the 0 level surface of this smooth function, right, has moved away proportional to the mean curvature of the domain, while here is moving inwards proportional to the mean curvature of the domain. So what Osher and Merriman does is, okay, we convolve with the Gaussian for an epsilon instant of time, and then we said enough of mixing. If the density is bigger than 0, then you go to the 1s, and if it's less than 0, you go to the minus 1. Okay, so they mix and segregate, and that generates movement by mean curvature. Okay, and so with Takis Uganidis wonder, okay, what happens if you are using a fractional heat equation? In other words, if you are mixing with a kernel, right, which has a long tail. In other words, what happens if you convolve with h to the s, right, x squared plus h squared to the n plus s over 2. Okay? So, so for instance, if s is 1, this is the Poisson kernel. The Poisson kernel corresponds to heat diffusion by Laplacian to the 1/2. In other words, the fundamental solution for Laplace convolving with the Poisson kernel is extending a function into its harmonic extension in the upper half plane. But also convolving with the Poisson kernel is doing ut equal Laplacian to the 1/2. Okay? So we ask what happens if we convolve with this kernel, right, and do this trick of convolving and segregating, convolving and segregation. Okay? The answer is that for S bigger or equal than 1, including 1 is the Poisson kernel, is the half Laplacian. The answer is that you obtain again movement by mean curvature. Okay, so nothing has changed. But if you go to S less than 1/2, then the movement is a movement by something like an integral curvature condition. Okay, so for S, notice that S bigger or equal than or bigger than 1 is the finite moment, first moment condition, right? That they put and they end up with an infinitesimal condition for the interface. Okay, but if you put S less than 1/2, then the speed of the free boundary at a point, so let's take the origin, right? The speed of the free boundary at a point is S at 0, right, is proportional to the integral of the characteristic function of the set at y minus characteristic function of the complement at y over y to the n plus s. Okay? And let me explain you why is this sort of an integral mean curvature. Okay? It's an integral mean curvature because let me write this in polar coordinates. Okay? If I write in polar coordinates, then this becomes the integral of r to the n plus s, r to the n minus 1, dr, the sigma, and here what do I have? So here I have the following. I have to normalize the sphere to the sphere of size 1, right? It's a normalization, so I have differential of area on the unit sphere, the normalized sphere, this sigma, differential of angle, right? Times, and then I integrate 1 in the set and minus 1 in the other. So this is what we were saying before, is the defect of the surface to be a plane. In other words, if there is more 1 than minus 1, this integral is going to be positive. Okay? If this is Lipschitz, this integral is going to diverge because I have, n plus s, right? If this is Lipschitz, this integral is going to diverge because I have minus 1 minus s, but here I have something which is of order 1. Okay? If this is C2, then here I have something of order r, and since s is less than 1, this is going to converge. So this integral, in some sense, distinguishes or sort of is diffusion-like, right? In the sense I was discussing before, in the sense that if the excess of 1s is bigger than the minus 1 in this integral fashion, the surface is going to move in that direction, okay? If not in the opposite direction. And so a natural question then is to ask, what are the minimal surfaces for this problem? Okay? And the minimal surfaces for these problems then are the ones that minimize, so this is HS, are the ones that minimize the HS over 2 norm of the set. In other words, you want to look at the characteristic function of S at X minus characteristic function of S at Y squared times X minus Y to the n plus S, right? This is the HS over 2 norm, and you want to minimize this norm. Of course, you have to have boundary values for this. In other words, you want to, so you have a domain, you want to put extend X this way, right? And say, okay, among all of the possible characteristic functions here, I want to find the one that minimizes this quantity. Notice that if the h1/2 is the boundary values of a harmonic function, right? If you the gradient you square in the interior, this is equal to the h1/2 norm on the boundary, and you know, if you are a numerical analyst specialist, you know that h1/2 of a function with jumps is infinity, right? But precisely, right, s is less than 1, so s over 2 is less than 1/2. Okay, so when you get to 1/2, the theory changes, and is what I discussed before. So we look at these minimal surfaces, and we in collaboration with Ovidiu Savin and Jean-Michel Roquet-Joffre, we developed a regularity theory for these minimal surfaces. And so basically the regularity theory is, as at the very beginning of time you blow up, you show that the blow-ups are cones, you come back and you do an improvement of flatness, okay? And let me tell you what is the monotonicity, what is the monotone function here, right? So the monotone function here is the following, right? If you take h1 half, which is not good, right? We know that h1 half corresponds to the energy of the harmonic extension, okay? Now, but you cannot put h1 half of a function which is 1 and minus 1, okay? But if you go below, then you can do an extension. This is what I did with Luis Silvestre, where hs, right, hs over 2, that is, corresponds to an extension by an operator of the form c to the 1 minus s, c is this variable, right, gradient of capital U squared, dx dz, okay? So the quantity that you look at, right, that replaces the energy formula is the following. You take your 1 minus 1 configuration, you do the harmonic extension, right, you take the ball of radius r, right, and you do look at this energy in the ball of radius r, okay? So you look at the integral of c to the 1 minus s gradient U squared dx dz, right, divide by 1 over r. Instead of n minus 1, you have to divide by r. dr, you have to divide by r to the n minus s, right? And this quantity is monotone. You see the difference between the integral here and the integral here is that although this is confined, this sees everything, right? Because it's the harmonic extension, and therefore it has a way to see what happens, everything at infinity, right? Because you have to see what happens at infinity. So we show that this quantity is monotone. This implies that blow-ups are cones, right? Then you can show that in 2D, cones have to be lines, and therefore, in principle, what you expect is that the solutions are smooth, except on a set. I mean that in 2D, cones are lines. It's a separate paper of Valdinocci and Savin, but the consequence of that is that minimal surfaces, integral minimal surfaces are smooth, except on a set of singularities of Hausdorff dimension n minus 2. The improvement of flatness is a very delicate argument, and I think Ovidio cooked it up. It's because you have to improve flatness in a geometric scale, right? It's a very beautiful argument. Okay. So, okay, so, and then still there is one step left, right? And the last step left is then why don't we look at the change of phases as the problem that has gradient U squared on each side and the non-local energy, minimal energy, separating both domains, okay? And this is something that we just have done very recently with Ovidiu Savin and Enrico Valdinocci, both my students, many years ago, or some years ago, of which I'm very proud. So we look at the, so you want to look at the problem as before, where you have, let's say, u equal minus 1, u equal 1, right? And here you are looking at the, so here you are minimizing gradient, the integral of gradient u squared plus the S perimeter of the set, of the boundary of the set where u is bigger than 0. Okay? And so we basically they develop the same theory, and here then when we basically we have to again look at where is the monotonicity formula for the area, okay? And so the monotonicity area for the area is like a Weiss type monotonicity formula. Where you have to combine, right, the area part, the non-local area part, you have to look over here, and the area and the gradient U square part, you look over here. Okay, so the monotonicity formula is something like, there are constants that are special, you know, have very delicate constant, but basically is gradient, let me call here little u, and its extension capital U. So you look at gradient of little u square, right, over here. It comes from the energy term, right, plus the integral of z to the 1 minus s gradient u square, gradient u square. This is in the n-dimensional ball, let's say, of radius r, and this is in the n plus 1 dimensional ball of radius r.
Capital U is the extension.
Capital U is the extension, yeah. Yeah, this is the, as before, this is the area term. This is what the monotonicity in the area term, right? And this is the monotonicity in the, and so here you have to put 1 over r to the n minus 1 plus s between, or let's say minus 1 minus s. Okay, and here is a special constant that depends on dimension. And then you have minus the integral over b r n of u square. And here you have to normalize by 1 over r to the n plus 1 minus s. And so this quantity is monotone. At the end you can classify the global solutions to be cones, and you again have to make an argument. So you still have to make an argument to go from sort of flatness to regularity. And I'm done.
Okay.
Thank you very much.
Questions?
Yeah.
Couple of questions. So some kind of non-degeneracy.
Pardon?
Is there some sort of non-degeneracy aspect? I mean, you need to know that these cones are.
Well, no, because when you blow up, no, the cones are far from planes. It's usually you can prove in all of these arguments that if you are very close to a plane, you have a plane. In fact, for these minimal surfaces, we prove that with Baldinocci. We have a paper about the structure of cones, the fact that the cones are isolated.
I mean, the blow up. Don't you have to prevent that from becoming trivial or something like?
Well, trivial is a plane. That's good for me. This is not like the free bound, you know.
Yeah.
Oh, you mean about the U on both sides? Yeah. Okay, but the cones are not trivial. Both cones, one thing that you can prove is that cones have density of both sides. Like if you have a minimal surface, if for instance you have a minimal surface and you look at the set at one side and at the other and you cut it with a ball of radius r, so you give me an object of this, which you don't know if they are regular or not, but they are minimal. So it's very simple to prove that if you take a ball, then this set and this set have positive density. Yeah, this is very important also when you do the improvement of flatness and so on. And this is just by comparing, you know, this has more area than this because this is a minimal surface, and so you integrate and the radius and you show that that the density on both sides is strictly positive. Okay. Yeah.
So you have the integral curvature in that integral and the
Yeah.
standard Dirichlet integral. Wouldn't
Yeah.
it be more natural to have HS norm, for instance, instead of gradient U squared?
You mean an HS norm?
Yeah, HS norm, yeah.
Well, yeah, that's a nice problem to do. I don't know. We just took this. This is okay. It is. You have to look again at the papers of 5 and Leibovitz and all the papers on phase transitions and decide what is determinant for what. In other words, what is determinant for the free boundary condition and what is determinant inside. For instance, I think this is what the engineers told me. I don't know, but I'm not so sure. But for instance, if you have a elastic material that is cooling or something like that, then locally it satisfies an infinitesimal equation. But the influence on the shape of the phase transition is global. In fact, many integral equations, like the quasi-geostrophic equations and so on, come from having a surface, right, that you have on one side a nice operator and the other a nice operator, but the influence on the surface is through the Neumann, Dirichlet to Neumann, let's say. And so it's integral, the equation on the surface is integral. Yeah.
This last monotonicity formula you wrote, the capital U is the extension of psi U positive or the extension?
Is the extension of little u. There is this extension theorem we prove with Silvestre that you extend, you take a, if you take a function in HS, right? I mean, you take the Laplacian, the S Laplacian on a surface, that corresponds to the normal derivative and an associated operator with a weight in Y.
The extension of U, not the psi U positive.
The extension of little u on the positive part, yeah.
So that is the Weiss formula.
Pardon?
It's Weiss.
This is a Weiss type formula, let's say, yeah. Yeah, this is a Weiss type formula, so I wanted to give.
And it's not
Yeah.
possible to write this part which has the capital U inside in terms of the original U somehow?
Okay, we did this extension because this is much, much better. And the reason is that if you try to write this integral in terms of the capital U, U is convolving with the Poisson kernel. So it's sort of all of the properties of U, how U at infinity influences this region, right? Here has integral form. So it's very difficult to estimate, to control precisely. But if you look at it here, right, this in some sense, because of this extension property, this in some sense concentrates all the information which is non-local in a local setting, okay? For instance, one of the things we prove that we don't know how to prove otherwise is for the string obstacle, this Almgren monotonicity formula. You prove an Almgren monotonicity formula in the extension is the standard one. If you try to reproduce that for using the data, then everything becomes some integral at infinity and it's much harder to control.
Okay, so, all right, so I would like to thank Luis again for
Thank you.